Okay, the last video got cut off a little bit, so I'm just going to finish very quickly this. The last thing we needed to get was the X bar, and for area 3, which is this one over here. And so we have 1/3 of 1, so that's 0.33 to get to the centroid of area 3. And then we add 2 meters to it, so it's 2.33. And we now have all these values. We plug them into these equations, and we get 1.61 for X bar, 2.1 for Y bar, and so the point is approximately there with those coordinates. We have to keep the coordinate system at the same place. We can't move around the coordinate system, so we keep the coordinate system at the same place that we began. Okay, for moment of inertia, let me just say that the moment of inertia is a definition. In other words, it's not a theory. And what happened was that this term, and I'm going to give it to you right here, Ixx is equal to the integral of y squared dA, and Iyy is the integral of x squared dA. What happened was that when mathematicians were developing formulas a long time ago, they kept on running into these terms, and basically they just said, let's give a name to them so that we can communicate easily. And so don't think too much about the meaning of moment of inertia. I'm going to show you how to calculate it, and all you eventually need to know is what makes it bigger and what makes it smaller, and that's about it. Don't think about exactly what it means. And part of the reason is that the units are unusual. I mean, you can sort of explain with it. The units are length to the 4th power, such as feet to the 4th, meters to the 4th, centimeters to the 4th, inches to the 4th. Well, what does that mean? I mean, if I have, I have feet, that's what? That's length. If I have feet squared, you can at least relate to area. Feet cubed, volume. But feet to the 4th? Yeah, it's hard to envision what that means. So that sort of illustrates that what I'm saying is don't think too much about the meaning of moment of inertia. Like I say, you want to know how to calculate it, and you want to know what makes it bigger, what makes it smaller. That's good enough. Okay, so what is, I have created these definitions, but I haven't quite explained what exactly they are. But I want to point out that moment of inertia is a property, in a sense, similar to length, area, location of centroid, volume. Okay, in other words, it's a property, and the difference is, so in other words, you're going to have, for instance, an area, and you want to know what's its moment of inertia. Well, and so you could say, look, it's like an area, like the area, but moment of inertia is reference to an axis, all right, which makes it different from others. Now, the impact of it being referenced to an axis, in other words, we have to say an axis. So in other words, Ixx means we have the moment of inertia about the x-axis. So in a sense, we're using the term moment about. Iyy is the moment of inertia about the y-axis. So we have to have an axis. I'm just showing these two as examples, but we could take any axis. And in other words, if I look at this particular area down here, I could take this axis, which are the Ixx and Iyy, but I could also take an axis here, an axis here, an axis here. an axis over here, an axis way down here, an axis way up here. Any axis we want, we can take the moment inertia about that axis. So the end result is that each body has an infinite number of moments of inertia because there are an infinite number of axes that can be used. So whenever we refer to a moment of inertia, we must reference the axis that we're using. So we can't just say the moment of inertia of this body is something. We have to say the moment of inertia about a particular axis is something. So moment of inertia a little bit different. So in other words, if I look at these two situations are the same shape, but my IXX and IYY for both of these are different because here's the x-axis in this one, but the x-axis over here is a completely different location relative to the body. So I would get different moments of inertia for this. I would get different, I say, IXX and a different IYY for these two situations. So, because the axes are located differently with respect to the body. Now, I'll just make a comment about our dA when we take a dA. And I'll just note that, as you know from your calculus classes, that we can take dA in a number of different ways. Here are a few. I could take my dA like this. I could take it like that. I can also take it as this little point. So the dA in this can be done in different ways. So like I say, I is always about an axis. You must specify the axis. Okay, so we're just going to get right into it here and do this example, which is to get the moment of inertia for this about the x-axis. So here's my x-axis right there. I want to take the moment of inertia of this rectangle about this axis. And I guess I didn't quite show it, but just to make sure that, well, I'll just say it. This is at the in this particular case, the origin is at the center of the rectangle. So, which is, of course, right there. That origin is at the center of the rectangle. Now, so we're going to take IXX. Here's my XX axis that passes through the center of the rectangle, as shown. And I'm going to take the dA like this. So like I say, there's a number of ways we could take the dA. We could take it that way, we could take it that way, or we could take a little tiny square here, but we're going to take it like this. If I take it like that, then my dA is equal to B times dy. So now, so my dA is B dy, my IXX is the integral of y squared dA, which means it's the integral of y squared B dy. And I can take, the B is constant, so I take it out of the integral. And so it's going to be B times the integral of y squared dy, y squared dy, and I'm taking it from negative h over 2 to positive h over 2. So from negative h over 2 to positive h over 2, this is y squared. The integral of that gives me y cubed over 3. I evaluate it between h over 2 and negative h over 2. So just plugging that in, I get this expression, which we can reduce to this, bh cubed over 12. So what we find is IXX is going to be 1/12 bh cubed. That's the typical way people express it. You should memorize this. So this is the moment of inertia of a rectangle about an axis that goes through its center. So it's I about the center of the rectangle. You know, and we have to say that it's a horizontal axis. Okay, now suppose we put the rectangle here, and now we want to find IXX. So we have a different axis, same area, which is B times H, but now it's a different axis. Well, what does that mean? So again, I have my integral, which is the integral of y squared dA, which again I'm taking my dA is going to be, again, dA is equal to b dy, which means what? Which means that I come to the same spot that I was before, except that I'm now going to integrate between 0 and h, because now I'm at 0 to h. Again, it's b times y cubed over 3, evaluated between 0 and h, which gives me just 1/3 bh cubed. And the previous result was 1/12 bh cubed. So there's a, that's the difference, 1/3. So now what I want to do is introduce what's called the parallel axis theorem, which you may have seen in your math class. And here's the theorem, is that the I about a parallel axis is the I about a centroidal axis plus d squared a. So what do we mean by that? So this is a good thing to memorize along with the 1/12 bh cubed. So I think I asked you to memorize the, just to make sure, memorize this 1/12 bh. It's going to be convenient for you. You're going to use that one, 1/12 bh cubed. And then the parallel axis theorem being I about a parallel axis is the I about the centroidal axis, and I just add d squared a. So what is d squared a? We'll get into that. But, well, d is the distance between parallel axes. And, okay, so I'm not going to derive this, but I will verify for our case. So what does that mean? So let's look at, so this is going to explain to you exactly what it means. We had the rectangle. We took an x-axis through the centroid, or the center of that rectangle, and we got 1/12 bh cubed. Then we took the moment of inertia about this axis down here. Now notice, these two axes are parallel. So that fits my parallel axis theorem. I have to have axes that are parallel. And this 1/12 bh cubed, notice, that is my centroidal axis moment of inertia. So now, what is the definition of d? D is the distance between the two parallel axes. So the d is the distance. There's my centroidal axis, there's my other axis, and that's my d, the distance between those two parallel axes. So in this case, d is equal to h over 2. So if this theorem works, then I should be able to take this d, put it in there, and my a, of course, is simply the a of this whole thing, which is a is equal to b times h. So what should be true if this theorem works is that I take the I about the centroidal axis, which is that. I, the parallel axis, is this one. D is here. and A is equal to B times H. So if I substitute all those things, then I should get an equality here. Let's see if we get it. So the 1/3 BH cubed goes here. The 1/12 BH cubed goes here. And then my D squared is going to be H over 2 squared. And my area is B times H. So the question is this true? And if we simplify this, this becomes 1/4 BH cubed. And if I add 1/12 BH cubed to 1/4 BH cubed, I get 1/3 BH cubed. And what do I see? Oh, it's the same. So I get that it's true. So this is not a proof, it's just a verify for our case. So I'm not going to go through the proof of this. I'm just going to verify it at this stage. You can try it yourself for other cases. Okay, here's a homework problem for you. I want to find the moment of inertia. So first of all, two things. First, I'm going to find the centroid of this shape using the coordinate system shown. Okay, so there's my coordinate system. I want you to find the centroid. Well, this is all symmetric. Everything's symmetric here. So the centroid is going to be along that symmetric axis. So you don't have to get where the centroid is in the x direction. So you don't need x bar. I can tell you what x bar is immediately because this is 0.6, and given where our coordinate system is, that means that my, x bar equals 0.3. It's okay to make these 0.3 meters. It's okay to use common sense, and if everything's symmetric, just use it. But you have to use it right. Don't make an assumption that is incorrect. So you have to be able to identify that you really have symmetry. What I've seen in students is they start calling everything symmetrical when it's not. So, just be careful with it is about all I can say. Okay, so we're going to find the centroid of the shape. In other words, we need to find what is y bar, because it's going to be someplace along here. Is it going to be here? Is it there? Is it there? Is it up here? So first thing is to find the centroid of the shape. And, the coordinate system is down here. And then find the moment of inertia for a horizontal axis that passes through that centroid. And I want you to do it by filling out the table and using the equations shown. So I've given you this table here because this is the easiest way to compute all this stuff. So this is area 1, this is area 2, this is area 3, and all you have to do is write B1H1. So what is that? I'll get you started. 0.6 times 0.2 and 0.2. And then A1 is what? Is 0.6 times 0.2. And then y bar 1, what is that? Again, that's the distance to the centroid of the area we're considering, but it's the distance from the base down here to the centroid. Now, for this one, it's this distance. And for this one here, it's that distance. So that's my y bar 1. And then D1 is simply the overall y bar that we get using this. So this y bar goes right in there. y bar 1 goes in there. So d1 is y bar minus y bar 1. d2 would be y bar minus y bar 2. And d3 would be y bar minus y bar 3. So that gives me my d's, and by the way, don't worry whether it's plus or minus because it's going to get squared. It's going to get squared in my moment of inertia equation. So whether it's plus or minus doesn't matter to us because it's going to get squared. It's going to be a positive number anyway. Okay, so with what I've just said, I want you to fill out this table and calculate the y bar and calculate the I. Notice once you filled out this table, once you filled all these values in, then what? Then everything in this equation is known. Everything in this equation is known. So that's, and so we just plug it in. So if you get this right, all you have to do then is plug it into these equations and you'll be fine. So go ahead and pause the video here and do this one. Okay, so if I'm looking at this area here, what if B1 is 0.6, H1 is 0.2. And how do I get A1? A1 is going to be A1 equals B1 H1. So very straightforward. And then we go to area 2, and I have what? There's area 2 right here. I've got the B2, H2, and then the A2 for that is B2 times H2. So I know that my B2 is 0.08, the H2 is 0.4. So 0.08, 0.4, I multiply these two out, and I get A2 is 0.032. And then what is my y bar? Well, to get to here, it's going to be 0.2 for that, plus another 0.2 for the next portion to get my y bar 0.4, and then the next one is way up here. What is this distance is the question. So we always reference that to the x-axis consistently. So let's go to the second one. I guess I didn't do this. 0.08 for B, 0.4 for H. Multiply it out to get the A2. So in other words, 0.4 times 0.08 is 0.032. Y bar T based on y bar 2 based on what we just got done talking about is the distance here. And for 3, I'm up in here. B3, H3, you can all get. I multiply those two out, I get A3. Y bar 3 is this distance. This total distance. And that works out to be 0.65. And then again, I have my, so I can calculate my y bar by simply plugging into this, and I get 0.2646. Once I have the 0.2646, then I can get the d's, which are the distances between certain centroids. It's going to be the overall centroid. So remember how we defined it before. D is equal to, the distance of the overall centroid minus the area centroid. So what is this? This is, y bar minus y bar 1, for instance. So you've already computed y bar 1 previously, so you should be able to get the d. So once we are able to get these, so we get these d's, you can take a look at them, and again, the d, just to emphasize this, is the distance between centroids. So in other words, it's the overall centroid minus the centroid of that area. So again, our D would be the overall y bar minus y bar I, I'll call it I. So in our particular case, our overall y bar, our overall y bar is 0.2646. It goes in the first term in each one of these. And then the y bar 1 is 0.1. And the y bar 2 is 0.4, so I put that there. And the y bar 3 is 0.65, so I put that there. Once we have all these terms, then I can put them into this expression for I that I pointed out last time, and we solve and we get 0.01064 for the moment of inertia. For the centroid, notice that it's 0.2646 meters. Should write that down here. 0.0. So right there, right here, that gives me the location of that centroid right away, which is important for us. Okay, I'll stop there.